Okay, P-Chem, January 19th, it's Tuesday, and we are doing more work on quantum mechanics here today. So I want to direct our attention to a couple of things. Let's, first of all, talk about meaning of the wave function, continued. Let's start with a very simple case. We have a particle moving in one dimension, in this case that I'm envisioning, between x equals 0 and x equals L, a certain length in meters. And one might envision such a system as a thin piece of wire with an electron in it. So here's the electron, and it's on this thin piece of wire, and it really can't jump. That electron can't jump off the wire. It can't go off the end or the sides of the wire. The only place it can be is on this wire between x equals 0 and x equals L. Now, let's imagine that we can write a Hamiltonian for that particle. And as we know, that is the total energy operator. And if we want to solve Schrödinger's equation, of course, it's this Hamiltonian operating on the wave function to give an energy times the wave function back again. So that's Schrödinger's equation. And we know already that the probability of finding this electron between x and x plus dx, that probability has a very definite expression that goes like this. It's psi star of x times psi of x dx. That's the probability. And do you remember what we call the star from our earlier lecture? It's called, it's two words. I remember.
That's the complex conjugate.
Yeah, it is the complex conjugate. Is that star. And for right now, I just want you to remember this. And so the total probability let's get this let me get the spelling right. Probability of finding electron on entire wire is you add up all the probabilities over the whole distance. And how do you do that? This total probability equals 1. That says there's unit probability of finding our electron on the wire. It's got to be there somewhere between 0 and L in our example. And so we would sum up the probabilities. X goes from 0 to L of psi star of x, psi of x dx.
Which is equal to 1.
That's 1. That's 100% unit probability. If I add up all the probabilities off this whole wire, it's got to add up to unit probability. It's somewhere on that wire, okay? And by the way, the wire could be infinite in length, couldn't it? It doesn't have to stop at a finite L. This length could actually go out to infinity. We can have an infinite long wire. So let's just make a note. Could be finite or infinite. Okay. Wave functions are said to be normalized. And this is important because you can get something that obeys something that isn't normalized. They're normalized when the integral psi star psi dx over the appropriate range equals 1. In other words, a normalized wave function, if you integrate it over all the x values, it has to give 1 unit probability. And that makes good intuitive sense. That electron somewhere on that wire, all the probabilities have to add up. Okay. And so if a wave function is not normalized, one of the first things we may do to it is normalize that. And that'll be one of the early assignments that all of you do. Okay. Now, you might want to look at example 7.4. Because our book does give an example of how to normalize a wave function.
But shouldn't the total probability always be 1?
Over the entire range of x values, the probability should always be 1 if you're integrating over the whole thing.
Okay.
Now, you may integrate just over a portion of it,
Uh-huh.
which there are reasons to do that. But the answer is wave function should, in principle, be normalized. You shouldn't even work with unnormalized wave functions. There are a few cases where it's better not to, but most of the time it's much better to have normalized wave functions.
When you say normalize it, is that in the same sense of when you normalize a vector?
It's normalized means choose some constant out in front so that when you integrate over all the x values, you'll get 1.
Like all
Okay.
x values that exist or within your range?
Yeah, so for example, let's see what our book example is. Okay. Okay. So let's let psi of x equal AE to the I kx. Okay, this is a wave function. And we'll let x go from 0 to 2 pi. And we want to find a such that psi of x is normalized. So let's do that. In other words, we want 1 equals the integral of psi star psi, or psi of x star psi of x dx. X goes from 0 to 2 pi. So what we do is say, hey, this is the integral, x equals 0 to 2 pi of a e to the I k x star a e to the I k x dx. Do you see how I'm doing that complex conjugate? Now, this is good practice for us. How do I interpret that thing in square brackets, a e to the I k x star? What do I write next? In other words, if I want to do what that says, so it's x equals 0 to 2 pi. Complex conjugate always means replace I with minus I. Okay? Kind of remember that from...
Replace I with minus I.
Okay, so I goes with minus I. Star means replace the square root of -1 or I with minus I. And I've done that here. AE to the minus IKX times AE to the IKX dx. Now, we're almost here. That's a marvelous thing. You see what's going to happen to e to the minus AKX and e to the plus AKX when these two multiply together? So e to the minus a times e to the a equals e to the minus a plus a equals e to the 0 equals
Oh, they
1.
just get out of there, yeah.
So
That makes
this is going to become the integral x equals 0 to 2 pi of a squared dx. Okay? Which becomes a squared integral of that is x evaluated between 2 pi and 0. So a squared times 2 pi is the result of the integral. And strictly speaking, it's 2 pi minus 0 if you want, which equals a squared times 2 pi. Okay, so this whole thing I'm doing in ground is a normalization. And I'm choosing a different example from our book example, because the book example is a wonderful example, but I wanted to do something different.
Did you solve for a from there?
Yeah, that's exactly right. So at this point we say, okay, in order for it to be normalized, a squared times 2 pi has to equal 1. So you can say, well, this means that 1 equals a squared times 2 pi, or 1 over 2 pi equals a squared, or 1 over 2 pi to the 1/2 equals a, or 1, if, depending on how you want to write it, 1 over the square root of 2 pi. This is what's called, this a is now the normalization constant. And so our normalized wave function then is 1 over the square root of 2 pi e to the I k x.
Knowing that, although we know now how to do what you just showed us up to the integration part, are we able to just drop the e and go straight to, or actually no, because all the wave functions will equal something different, right? They're not always going to
Yeah,
equal
they'll
something
be
like
different
that.
values of k.
Okay.
Now, you'll still get a 1 over 2 pi in this particular one,
Okay.
but this is a
This
beautiful illustration of how you get a normalization constant.
Okay.
So the k doesn't affect the normalization, you just necessarily.
Right, and you can see why not, because with the complex conjugate of the function, whatever the k is, it drops out. And so, for this particular wave function, the 1 over square root of 2 pi applies to any of the wave functions. Okay, this is a lot to digest in one little hour, isn't it? Like, oh. Okay. Now, let's erase this board.
So I'm sorry, I understand how we found A. What is that really telling us though?
Okay, now, if you take this wave function
Mm-hmm.
and do psi star psi dx, x to 0 to 2 pi, that wave function will give you the unit probability.
Okay.
In other words, it is fully normalized now. When you integrate from 0 to 2 pi, those are our limits,
Yeah.
it will give you the value 1. You'll find that particle somewhere
Okay.
So,
between 0 and 2 pi.
so the value of a is just going to change based on the range that you select?
Yes, because the range kind of defines the quantum mechanical problem. Are you going from plus infinity to minus infinity? Are you going a meter? Are you going a centimeter? Are you going the distance of one chemical bond? That's determining what you do. So normalization is always with respect to a given x domain.
Because there's 4 possibilities for the wave function, right? And then, yeah, okay. So there's,
Okay, let me make sure I've addressed your question. You said something about,
yeah, since there's 4 different possibilities for that wave function,
e to the minus, or
Yeah, that's
cosine,
yeah.
or sine.
so there's going to be 4 different results of the integration. The only thing that changes is the range, though, right?
Yeah, now e to the minus ikx will also have a square root of 2 pi in there. and we'll see with cosines and sines what happens. Just add a thin metallic sheet. And the obvious thing to think about is a sheet of aluminum foil. And imagine, this is a perspective drawing, so imagine the I unit vector was here, the J unit vector is there, and this is the X coordinate, and J is the Y coordinate. We could have a wave function psi x y, which would be so I could have this go on in the x and the y direction, and I could be going, let's say, from 0 to Ly here, or let's do it here, 0 to Ly, and then we have an Lx right here. So in a two-dimensional wave function, I might have a simple case where the x and the y are separate, and there'd be some combined a, which would be ax and ay multiplied together, e to the I kx plus ky. Oh, let's see, kx x plus ky y. So in a two-dimensional wave function, what integrals would I use to normalize it? So here, in other words, we're kind of looking for an electron somewhere on this flat sheet, right? And on that flat sheet, we'd say, hey, 1 is the probability of finding that electron from x equals 0 to Lx, y equals 0 to Ly, psi star of x and y, psi of x and y, dx, dy. And we could do a three-dimensional metal cube, couldn't we? We have a triple integral for a cube. And we want to know what's the probability of finding this electron in a cube of copper with dimensions Lx, Ly, and Lz. So this condition says, if this is true, what do we say about this wave function, psi of x and y? Is this wave function normalized if this is true?
Yeah.
Yes, because when we integrate over all the y and all the x, we have unit probability of finding that electron somewhere in that sheet of aluminum foil. Okay? So, now let's see if you can do this. And Phoebe, aren't you glad you're safely a continent away and don't have to answer this question? So we have a solid cube, let's say, of copper or aluminum, and we have an electron somewhere, yeah, in the box. And we have unit vectors I, J, and K. And now if we have normalized wave functions, what that means is we'll have psi star. And now how many coordinates will the wave function depend on?
3.
3. What are they?
Are we doing I, J, and K?
Yeah, I is with X,
Yeah.
J is with Y, and K is with Z. And so we'll have psi star of the coordinates X, Y, Z times psi, the coordinates X, Y, Z, dx, dy, dz. Now, we don't just have one integral though, we're going to have a triple integral, aren't we? X equals 0 to Lx, x equals 0, or y equals 0 to Ly, and z equals 0 to Lz. And if this wave function is normalized, in other words, there's a unit probability of finding that electron in that three-dimensional cube of metal, whether it be aluminum or copper cube, what does this integral have to equal? 1. That's what we mean by a normalized wave function. So, whatever the limits are, however many coordinates are in the wave function, if we go over the whole range that that electron or whatever particle it is can go in, the sum of all the probabilities has to equal 1. Now let's go back to our book example on normalizing a wave function. They have some other type integrals that they're talking about. Good discussion on page 264 and 265. All right. That was a big thing to get normalization done. Super important. Okay. Now, let's go on here. Take just a moment to erase the board. Okay, let's talk about quantum operators. We already know that that's minus h bar squared over 2 times the mass of the particle, d squared, dx squared. This is a curvature operator on the matter wave. The potential energy operator varies. It can be all sorts of things. It can be a constant. It can have this functional form. It can have that functional form. So this is the kinetic energy operator. We'll concern ourselves with one dimension to start with. This is the potential energy operator. And have a wide variety of forms. Now we'll look at several common forms in the not too distant future. So this is our potential energy operator. And do you remember what these little coolie hats are? Means operator. Now, there is an operator P of x that's a linear momentum operator. And this one is called the position operator. And we can have angular momentum operators. We can do all sorts of interesting things.
What's the point of making an operator? Like, how does that affect things?
The operator operates on the wave function and tells us certain things about the quantum system. You've asked an extremely good question. So, this is just a few of the most important ones. We have the angular momentum operator, R cross P. We have all sorts of other operators. But we want to work with these. I want to know, though, a question. What if you have, this is all, deliberately so I might add, this is all for one-dimensional. Systems. What do you do with a two-dimensional system? What does the kinetic energy operator look like in Cartesian coordinates? So I'm interested in one particle, two coordinates. Obviously, the kinetic energy is going to be a function of whether you go along in the x direction or in the y direction, right?
Mm-hmm.
Okay, so how would we write this two-dimensional kinetic energy operator? And this goes to you at
or square that whole thing? No?
no, that not an unreasonable guess, but there's the kinetic energy in the x direction.
Yeah.
If you summed up the kinetic energy in the x direction and in the y direction, would you have it?
You have to find.
If you know the x kinetic energy and the y, so if this room, if that's 0, 0, this corner, and I'm walking at an angle like this.
That's the sum of the x and y.
Yes! Okay. So how would I write that? I'd say, well, that's Tx plus Ty.
Okay. That makes sense.
Okay, and we could put the expression in, minus h bar squared over 2m d dx minus h bar squared over 2m d dy. What's the m?
Mass.
Mass of what?
Particle.
Okay, so this is a one-dimensional, a two-dimensional system, one particle of mass m and two coordinates, x and y. It's free to go on this sheet of aluminum foil. We have an electron that can go anywhere at once. It can have x and y kinetic energy.
Should those be d squared, dx?
Oh, wait a minute. These are need to be squared. Yes. Sorry. Okay, now, the potential energy operator is also a function of x and y. And we said in a previous lecture that all the unique attributes of a system, to a certain extent, come to life in the potential energy operator. Are these completely separate? Is the potential energy zero? Must make a choice on details. Now, what's the position operator? Here it's just x.
Is it a plane?
Yeah, it's kind of like, so the position operator is kind of like r, which equals what? X plus y operator. In other words, you have a vector r with an x component and a y component, and you treat that quantum mechanically as your operator is really x plus y. By the way, that's what coordinates do. If this corner is the origin of a coordinate system, and I go x steps this way, and y steps this way, the vector r comes directly from that corner to where I am. And so a two-dimensional position operator is x plus y. Okay? And then what about a momentum operator?
It's just the same thing, but adding it with respect to d of dy.
Yeah, I think you're on it here. Momentum in two dimensions. You have a momentum operator comprised of an x operator and a y operator. This is minus h bar over I d dx minus h bar over I d dy, first derivative operator. And that is our linear momentum. And we can do other operators. Suffice it to say that in quantum mechanics,
So it's supposed to be negative.
I thought
oh,
you're adding that.
no, these should be positive. Convince yourselves this is true. Minus I h bar d dx equals h bar over I d dx. You can prove that if you multiply the numerator and the denominator by I times I is -1 times 1 is 1. and you pulled it underneath. Does that make sense, Si? Like I can prove this equals that.
Yeah, okay.
High school.
About that, yeah.
But I'm sure if we messed around with it enough, we'll understand exactly.
Yeah.
Uh-huh. Right, so what I'm doing is
Yeah. That's like a random thing they teach you now.
minus
that you've never
ix equals x over I. That's kind of what I'm proving. Here's the steps in the proof real quickly. I multiply both sides through by I. I do the resultant algebra, these cancel out. I times I is minus 1, so this equals what? I times minus I is plus 1, so x equals x. So that proves this. And that's why I changed the sign back again. This is right, so is, and you'll see them in both confirmations. Okay, so we've done one particle in multiple dimensions. We're starting to get a hang. You have to have an operator that covers each dimension, and the wave function covers each dimension. So typically in a three-dimensional space, if you have one particle, you'll have three coordinates, an x, a y, and a z. Or if you're in spherical polar, an r, a theta, or a phi. Or if you're in cylindrical, an r, let's say an r, phi, and z, depending on how you define those coordinates. All right, so now what do we do?
Work with problems?
Oh, we have one more little thing to do. What happens?
We never really messed around with potential energy.
Oh, well, don't worry, you have a whole semester to do that. You'll see more potential energy than you ever wanted to.
Okay.
Okay, what if you have a multi-particle system? And every particle can be in 3 dimensions.
Ooh. They're not moving together, they're just kind of going crazy.
Yeah, so let's... Okay, so if you look at something like, okay, let's look at atomic lithium. Okay. So we're looking at the electrons only. We'll assume the nucleus is fixed. Okay. And we wanted the electronic, not the nuclear, electronic wave function of the electrons in a lithium atom. Just one atom of lithium. So we're in 3 dimensions. Now, how are we going to do that? In other words, every electron can go in 3 dimensions, right? So our wave function is going to be of the form. We have 3 electrons. And you can have it be in any coordinate system you want. But, so you can have R1, theta 1, phi 1. That's the coordinates of electron 1, but we have 2 other electrons. What do we write here?
I can't see where you are. Oh.
So R2,
R2,
theta 2,
R2,
All in one parenthesis.
theta 2, phi 2. Okay, so we got 2/3 of the coordinates. What's the other one, Ed?
R3,
That's right.
theta 3,
R3,
theta 3,
theta 3,
phi 3.
phi 3. Now, you look at the periodic table. You remember the water molecule with 18 electrons. You remember an organic molecule like benzene, which has a lot more than that. And then you start thinking about RNA and DNA. So for one atom of little baby lithium, we have a 9-dimensional wave function. And how do we do the probability that we'll find this electron somewhere within the space?
Computer.
How many integrals do you have?
9.
You have 9 integrals, so this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Psi star R1, R1 to phi 3, right? Psi R1 to phi 3. And over here you're going to have the R1, the theta 1, the phi 1, the R2, these should have commas, the theta 2, let's see, the R1, the theta 1, the phi 1, the R2, the theta 2, the phi 2, the R3, the theta 3, the phi 3. You'll have that many differential increments, and then you'll have all the integrals, whatever their limits are.
Are we missing? I feel like we're missing something.
Okay, let's check it. It could easily be R1 theta 1 phi 1, R2 theta
Oh no,
2
isn't
phi
like
2, R3 theta 3 phi 3.
this is spherical coordinates, right?
Right.
Aren't you supposed to plug in like the spherical, like sine phi squared?
Oh no, not yet.
Oh.
Not yet. I mean, I'm just doing poor spherical coordinate. Now, if I did it Cartesian, I'd have x1, y1, z1, x2, y2, z2, x3, y3, z3. Here I have r1 theta 1 phi 1, r2 theta 2.
No, I get that. Yeah.
So I still have 9 coordinates. I can choose which ones I can get. Okay, 3. Now, if you want to do general chemistry or general biology, are you going to think about 9-dimensional wave functions for a lithium atom? For a uranium atom, it'll be 92-dimensional wave functions. For carbon atoms,
6.
okay, it's 6 electrons, right, for carbon. That's ridiculous. Isn't that amazing? I mean, you've got to make approximations. You've got to do something other than a 9-dimensional normalization integral.
That doesn't look fun. I feel like, is that what they're doing when they're solving these types of equations?
Yeah, they have all this stuff in there,
Yeah.
in computers,
Computers.
when they solve it. And there's all these computer programs that are being developed, that have been developed, to do these kind of calculations. Absolutely crazy. But you need to know what the calculations mean in the first place.
Yeah.
That's the trick. And if this wave function is normalized, okay, so we have
There's one.
multiple particles, okay, So there's a unit probability of finding all the particles all the time over the range that we're going. That's what it means.
So to normalize it, it's the thing where you plug in the function like e to the ikx.
Right, and you'll find that in this one, it'll be a product, and very often a product of one-dimensional functions. And you just integrate term by term by term to normalize it. Okay? So we can have multi-dimensional integrals that are one particle of mass m, 2 or 3 coordinates. Here we have 3 particles, 3 electrons, let's say, each with an r theta and phi. And we have a 9-dimensional wave function. Depends on 9 different coordinates. And we're only at element number 3 in the periodic table. Oh my goodness.
So when they try to solve that, what exactly are they looking for? What are they solving for?
They're trying to get the wave functions and the energy levels.
Okay.
Because the energy levels can be related to chemistry, to thermodynamics, and to spectroscopy.
Okay.
And by the way, that's a pretty important combination.
Yeah.
You know, if it's going to affect chemistry,
Can
spectroscopy.
we review how they get the energy levels from that? I'm just trying to see the...
Oh, the energy levels are the in the H psi equals E psi, those are the E's.
Okay.
And by the way, those are important spectroscopically as well. Now, ever since you said you got the flu, my head's been killing me.
Dude, no.
You can't get sick. I can't afford to be sick. It's not in my calendar to be sick.
No.
Maybe it's psychosomatic.
It might be a little.
Oh, he's sick. Therefore I'm sick. Now, here's an interesting concept. The idea of the expectation value. And I don't know if you kind of notice this, we're kind of drawing together a whole bunch of quantum ideas. So here's a general quantum mechanical operator. It could be the kinetic energy operator. It could be the potential energy operator. It could be the Hamiltonian. It could be a position operator, linear momentum, angular momentum, you name it, it could be that. The expectation value, and now I'm just going to use one integral sign. It could be multiple coordinates. If the wave function is normalized, the expectation value of the operator, often symbolized by this, and this integration element is understood to encompass all coordinates. So in the case of lithium, with 3 electrons, d tau would be 9, there'd be 9 different coordinates embedded in there, but we don't write those everything. So the expectation value is, if you have normalized wave functions, you integrate the wave functions with respect to the operator.
D of, what is that again? Wave function D
Tau.
tau.
This is the Greek symbol tau.
G tau.
Okay? So we've learned about multiple dimension wave functions, multidimensional operators. We've learned about the expectation value. We've learned how to normalize a wave function. Man, we've done a lot of stuff, in case you hadn't noticed. Now, go ahead and shut that video off for just a second. Are you dialed in here?
We're dialed.
Okay. I wanted to draw your attention as we close today to page 280 of your text. It's right at the end of the chapter. And there's a checklist of key equations that you need to kind of know for this chapter. We've talked about a lot of these, but there's one that really caught my eye that I wanted to talk about. When you get a Schrodinger's equation, H psi equals E psi, you don't get one solution typically. You get a whole family of solutions, and it will indicate that by a quantum number n, which can symbolize any number of individual or combined quantum numbers. So our solutions are these sets of wave functions and their associated quantum energies. And this is an index, this n is an index for a quantum number. Now, you might, and everything I've talked about today, when I do psi star psi, it's the same n. So, for example, with normalization, it's psi n star psi n d tau. The n is the same on both of these for normalization. But one thing that summary equations on 280 points out that I want to point out to you is there's many solutions. So what if we had the nm one? It would look like this. Psi star n going with psi of m d tau. And if we've done this right, this is a general result, this will equal to 0 unless m equals n. Yeah. In other words, this is an orthogonality. Orthogonality condition. That the wave function star times another wave function, doesn't matter what it is, it's not the same one, you won't be able to normalize. Those two will be treated as mathematically orthogonal.
So what is m?
M would be like another integer. In other words, not the exact same quantum state. This thing will go to 0.
You keep saying these things, and I feel like I'm just like
Well,
talking about vectors. When you're thinking like orthogonal, I'm thinking like two perpendicular lines.
Now, but we have a definition of orthogonal. For us, the definition of orthogonal is this.
Okay.
And if n equals m,
Detail.
it equals 1. Which means they're parallel.
Oh, okay.
If n equals m, they're parallel in an abstract sense,
Yeah.
not in the sense of
A straight line.
Cartesian x, y, and z axes, but in an abstract mathematical sense.
Okay.
Okay, don't go looking for a Cartesian system. This is how we define it. That means orthogonal. This means normalized or parallel. Okay? Now, the Nobel Prize winning physicist, what did he say about quantum mechanics? The famous Richard Feynman at Caltech played the bongo drums, slept with every woman he could seduce.
I don't know if you told us already if this is the same person, but you said something in the lines of, if you think you understand.
No,
but you don't.
that's Feynman.
Yeah.
Okay.
Okay, so go ahead and quote it as best you can.
If you think you understand quantum mechanics, you're not doing it right.
Or
something
if
like
you
that.
think you understand quantum mechanics, you don't
You
understand,
don't understand
quantum
quantum
mechanics.
Yeah, something like that.
Okay, so in other words, if you think, oh yeah, I get this makes a lot of sense, you're lying through your teeth. This is hard stuff conceptually and mathematically. We've kind of cut you away from your anchor lines to reality. And, just what does this mean? What is this terminology? How do I use all this stuff? This is the very natural reaction of a serious, hard-working student first encountering this stuff. It's really confusing and hard to understand. So you're not doing as badly as you may think. Okay, let's take about a 10-minute break, and then